Hi everyone, my name is Huinvo and today I'm going to present my final project for Big Data Analytics course. My topic is energy efficiency. My topic and this dataset are related to energy efficiency, particularly the energy efficiency of housing. The dataset was obtained from this website right here. right here. The dataset relates how the size, shape, and other feature of a building can help or hurt the energy required to keep the internal temperature of the building, such as a home at a desired temperature. This is an important real-world problem that our energy-hungry society is only now beginning to look at it into details using data science tools. Some of the tools used to explore the data presented here were different visualization graphs provided through Rstudio tools and Azure machine learning for a more in-depth analysis. The machine learning tools were required to predict the response of the heating and cooling loads for different building parameters, such as relative compactness, surface area, glazing area. Azure machine learning and R are the main tools for this analysis. Through exploration of the data using these tools, I have concluded that many of the factors in the data help to determine the energy required to heat and cool building, but not all of them do. I have used R-core to see the correlation between given features. The R-core function The R-core function showed that there is a positive correlation between heating load and cooling load, meaning if the house does not require much heat to warm up, it does not require much air conditioning to cool down either. Through histograms and box plots created using ggplot package, I also see that the relative compactness, wall area, and the number of stories of the building and glazing area play a major role in determining the heating load and the cooling load. Besides visualization and after cleaning up the data, I test out Azure machine learning using a neural network regression model and a boost decision regression model to predict the outcome of heating load and cooling loads. The model were evaluated with a high coefficient of determination. Azure Machine Learning is one of the more powerful tools for more prediction. Azure Machine Learning is easy to use. The models are loaded automatically, highly visualized, and most importantly, it requires minimal to no installation. Azure Machine Learning is an online platform owned by Microsoft. They do very well in terms of organization and has a very gentle learning curve. It is open source. The only con is that for a free account, there is a limit for storage and speed when training the data. If you would like to analyze data that is bigger than 10 megabytes, you will have to purchase a premium account and your data will be processed with a faster speed. So that was my introduction, and as you can see, this is the data that was obtained from this linked right here. Through that, you will see that from column A to J, there is no title, that column names. So for the attributions, the first one is the relative compactness. Second one is surface area, wall area, next roof area, overall height, orientation, glazing area. As you can see, all things are listed here with the units belonging to the column. So the data set tell us of these values right here. If you notice, the X6 and X8 have a very interesting data. They have the value of 1, 2, 3, 4, 5, something like that. And X6 is the orientation. If you see that 2 is actually north, east, southwest for representing 2, 3, 4, 5. and for x8, 1, 2, 3, 4, 5 is uniform north, east, south, west. So just keep that in mind. They are categorical. So what I'm trying to do today is try to measure the transparency of the building. I'm going to use these 8 features to predict each of the 2 responses, heating load and the cooling load. And I will show the models that I use to do that and evaluate the models. So as I mentioned earlier, Rstudio, Azure Machine Learning, R functions are the main tools that I used. So now in order to analyze the data, I need to see what are given to me. So I explore the data using correlation. As you can see, I'm using RCore function, and what I see right here is the heating load and the cooling load. I see that relative compactness have high correlation. The overall height is also have a high correlation here, as well as wall area. However, the surface area and roof area tend to have negative correlation. Okay, but this is raw data. I mean, it is what it is. I also graph the correlation so that you can see that the blue is a positive correlation and the red -1. The red is a negative correlation. So the color, the intensity of the color tells how much correlated. The more intense color, the more related, I guess. So exploring the data. So now I'm just gonna do the graph histogram just to see each value, each column, and how are the values spread out, the distribution, I guess. So this is the heating load. You see that? Oh, okay. And this is the cooling load. If you notice that there are some very good number over here, the less heating load and the less cooling load, the better. That is our goal in general. So this one, what I did was I convert overall height. Oh, it's not here. Overall height values. So if you notice, let's see, overall height is x5, and in x5 you see that there's only 2 different kind of values, 3.5 and 7, because 3.5 meter and 7 meters. 3.5 meters is 1 story and 7 meters is 2 stories. So I rename the columns to 1 story and 2 stories, and then I graph the box plot for heating load and cooling load, and you see that 1 stories tend to have better lower heating load and cooling load, which are better compared to the 2 stories. Now in terms of the orientation versus heating load and cooling load, you see that orientation doesn't really affect the data. You will see that regardless of the direction of your building, the heating load and cooling load stay the same. Now for the glazing area, you will see that the more we glaze, the worse heating load and cooling load. We try, like I said, we try to get the minimum value, and as you see that the more glazing area, the more heating and cooling we have to consume. And this is the glazing area distribution, and you've noticed that without glazing has the best value, has the lowest heating load and cooling load value. In terms of the wall area compared to heating load and cooling load, the data doesn't tell me if the thicker the wall, the better the heating load and cooling load. I don't see that. As you can see, that is inconsistent in terms of the what the data tell me. So now I'm going to use Azure Machine Learning tool, and I'm going to predict the response of heating load and cooling load using neural network regression and boost decision tree. I supposed to have this slides right after this one, because this is a combination of roof area, wall area, surface area, and glazing area all combined to see how it responds together, correlated to the heating and the cooling. And as you see that they have positive correlation right there, so it tells that the heating load and cooling load efficiency has a positive efficiency by roof area, wall area, surface area, and glazing area. All right, so now is when I do the Azure machine learning with the two different models. How to choose models? The target to choose model is the model that fit well with the data. It has to be accurate, interpretable, fast, and scalable. That's all depends on what types of data you try to analyze. So I use this sheet to decide which model I should use, and because so this is where I base on when I choose the model. So now I'm gonna show you a demo of how I run my Azure machine learning. I import the data in here, and then I have some R script. The reason I have this because, as you know, the original data doesn't have column names or anything, so I just cleansing step for the data pretty much. After that, I get to choose the column that I think that it helpful for the model to predict. So what I chose is relative compactness, wall area, glazing area, stories, orientation, glazing area, distribution, heating load, and cooling load. As you know, heating load and cooling load are the labels that we're trying to predict, and the rest are the categories, the values that we use to predict heating load and cooling load. I normalize wall area and glazing area because their values is big, so I try to normalize all information pretty much. So after that, I split my let's see how everything looks up until now. So you see all the values here, and because they are normalized, so it's provide different values. I added some columns here, changing 1, 2, 3, 4, 5 to 2 to 1, stories and orientation. I list the real orientation of the buildings. So is the glazing distribution, as you see. Instead of just 1, 2, 3, 4, 5, and it can be confusing and might think that it's a numeric, but it's actually categories label. Yeah. So I use neural network regression to predict the heating load. I use boost decision tree regression to predict the cooling load. I purposely do this so I can demonstrate both of the models. I did cross-validate model as well. I also have the permutation feature importance. It will tell which features are most important. And then I score my model, and then I evaluate it. So now I'm gonna run it. It usually takes a while because this is a free account. And you will see that this is the flow chart of how Azure machine learning works. It will go from up here, down, and it's all based on the connections that we created. Okay, so now it's all set. You can see, so this one I'm training the heating load. So let's see, it will provide a score model. So there will be an extra column right here, and it's basically predicting the heating load, and this is the actual heating load. So as you see that it's really close. So this is a good model for this data. And let's see, what about this one? This is the cooling load, and I use a different regression model. cooling load 14. This is also very close, so these two models are good for this sort of data. And now we're gonna evaluate the model. Okay, so as you can see, the coefficient of determination is pretty nice, 0.98, almost close to 1. It tells that it's a good model, and I can use it to predict. And this one is good as well, 0.984. So thank you very much. So that is what this is my project. Let's see what else. Yeah, that is all. Thank you. Bye. Happy holidays.